Very good morning to all of you. On behalf of IHMTC 2021 conference, I heartily welcome Dr. Nicholas Huck from Comsol Multiphysics. Currently, he is the head of their development team at Comsol France, and he's working there since 2004. He's also the technology director of the heat transfer module there. And before that, before joining Comsol, he did his engineering in NCMAC before receiving his PhD in living system modeling from Joseph Fourier University. So please join me in welcoming Dr. Nicholas Huck from Comsol Multiphysics, who is going to give a talk on simulation for heat transfer and fluid flow applications using Comsol Multiphysics. So I hand over the session to Nicholas. Please start your presentation.
Thank you very much, Dr. Laxman Mala. And hi, everyone. I'm really happy to participate, say hello today. So as you said, I'm been at Comsol for 17 years now and in charge of development in France and development for heat transfer for Comsol in the world. So today, here is the agenda. We have a half an hour. I'll talk for 25 minutes and then I'll save some time for a Q&A session. So please ask questions during the presentation. I'll take as much as I can at the end. So we will discuss about modeling, the approach of Comsol for modeling and simulation, with highlights on non-summer flow, surface-to-surface radiation, phase change, multiphysics coupling, and I hope to also to be able to explain how this can be combined with optimization tools. And on top of it, I took the challenge to define and solve live a model, so that if you have never seen Comsol Multiphysics user interface, you will have at least a small experience. So Comsol is present across the world through several offices, including one in India, as you can see on this map. Comsol started in Sweden, in Europe, and now it's present all over the world through offices and distributors. So when we say Comsol Multiphysics, we also refer to a set of specialized modules on different fields. So as you can see on this slide, there are several modules. Most of them are related to different physics, electromagnetic, structural mechanics, fluid and heat. That's what we will mostly discuss today, but also chemicals. We have a few multi-purpose modules like optimization module and interfacing module to interface, as the name says, Comsol Multiphysics with different softwares. The idea at Comsol is to tackle the complexity of the real world through multiphysics. So you can either base your model on single physics and work on it, but of course you can also add several physics from the predefined physics interface. There is also equation mode where you can type your own equation for more flexibility, and you are really free to combine all of this and to solve your model. So when you solve your model, you can stay in Comsol Multiphysics and work from it. And there is also an option to create applications. So applications are tailored applications dedicated to particular physics, but are usually very easy to use thanks to a dedicated user interface. And this application can be made available through a server on the web, or they can be compiled for standalone applications. So that's our view of simulation: great flexibility to represent the real world, and then sharing the result either through Comsol Multiphysics or dedicated applications. Okay, so now I am jumping in the core of the topics and starting with non-summer flow, which is probably one of the subjects that has been the most discussed at this conference. So for Comsol Multiphysics, it comes as a predefined multiphysics coupling, and there are several versions of the same physics, but with a different flow regime. For example, from creeping flow to turbulent flow, free flow, or porous media flow, laminar, or turbulence, low or high Mach number flow, and in all the case, it can be coupled with the temperature of a surrounding couplings. And even if we have many flavor of this multiphysics coupling, they share all the physics property. And so, as I say, there are several flavors. And for example, if we look at the turbulence model, it starts by complexity of numerical cost with algebraic turbulence model, and go to LES with a lot of intermediate in these options. But regardless the option you select, as I said, these physics share the same options, and one very important is the ability to account for natural convection, which is available through the density definition. So this is how Comsol multiphysics user interface looks like. And as you can see, you have different nodes describing the physics. In the different nodes, you activate the option you want to work with, here the gravity, for example. And from that, you get access to a gravity node where you can define the acceleration of gravity. So as you can see here, if you are familiar with the equation, you can expand this equation tab where we recall the equation you are solving. So this is just a display, and there is also an option to display and edit the equation you are solving, so that you can also modify the equation you are working with. And I'm not going to give all the options, but just the classical physical phenomena we get requests for. So if you're interested to save some computational cost, maybe you would like to work with incompressible formulation of Navier-Stokes equation and still account for natural convection. So that's what is available through the Boussinesq approximation. And among the very classical physics, you want to capture, there is of course viscous dissipation, so the transformation of kinetic energy into internal energy due to the viscous stresses. And here again, I'm recalling the equation, but of course, as a Comsol user, you don't need to know the equation. You can check them, of course, if you want, but otherwise you just activate the corresponding option. And for pressure work, in this case, this is built in the equation. That's not really something you can enable or disable. As soon as you work with a compressible flow, it will be present in your model. And that's exactly the same with the Joule-Thomson effect. As soon as you're working with compressible flow, and provided the Joule-Thomson coefficient is not null. So, for example, provided you are not working with ideal gas, then you will account for Joule-Thomson effect. And here we show the result of a tutorial that is available in our library. And this is an opportunity to say that all the illustration you see on my slides, they are coming from models that are available through our website. So yeah, assume that you want to know more about Joule-Thomson effect, just go on comsol.com, and in the model gallery, type Joule-Thomson. I'm sure you'll find this model. Okay, and I'm as soon as we are talking about temperature, we think about conduction, convection, of course, but you know that radiation is another mean of heat transfer, and that's something really important. I like to include it in the model, so I'm going to take time to present also how and what you can expect from Comsol multiphysics when it comes to surface-to-surface radiation. And I have this opportunity, maybe if you're following Comsol multiphysics actuality, you have seen that we just released a new version, Comsol 6.0. And in this version, we made very good improvement for surface-to-surface radiation, which make it very fast and easy to include in your model. So when I'm saying surface-to-surface radiation, so I'm just focusing on transparent media. I'm not talking today about semi-transparent or participating media, but that's something that is covered as well. So if I go back to surface-to-space radiation, Comsol multiphysics is able to account for surface emissivity or absorptivity, diffuse reflection, specular reflectivity, and transmissivity for in case you have a semi-transparent surface. So all these properties are part of your model. And this property, so again, if you go in a model and select the corresponding model, all these property can be defined in the user interface. In case you have a shell with two red distinct face, you can of course define different property on each face. And I believe that's something where Comsol is really interesting for, is that the definition of material property and surface property in particular can be defined, I mean, from virtually anything if you are able to write with pen and paper an expression that couples surface emissivity, for example, with temperature, then you can just type the corresponding expression. It can be a function of the spatial coordinate of time in case you have, I don't know, a change in the surface property along time. It can be a function of time. It can be a function of another dependent variable like chemical composition of something present on the surface. It can be a function of angle of incidence of the irradiation. And so, as I said, you can combine analytical expression with user-defined function, as we can see in this screenshot here. And in case you want to model something more advanced than gray surface, we have a solar and ambient surface, which is very convenient and fits a lot of needs where you want to define material property for the solar radiation and another set of material property for the infrared. That's we'll see on the next slide. That's, for example, useful to model the greenhouse effect. And at Comsol, we also have a third option, which is called a multiple spectral band, which make it possible to have an arbitrary number of spectral bands to define surface property for each spectral band. And it is very flexible. Of course, the limit to this is the cost. The more spectral band you have, the more you have to solve, and also the more material property you have to define. So I would say that's the only limit. And all the other dependency, like temperature, spatial, or dependent variable dependency, can be defined, can be combined with wavelength dependency. So in the user interface, you have different approach to define that. Either you have a library or material property that are already wavelengths dependent. So in this case, you just pick a material property from material. You can also decide to have a constant material property per spectral band. So in this case, you just type a constant, or you can also type an expression per spectral band. And last option is to get to use a function that is a function of a spectral band. And then you just type an expression that is the same for all spectral band, but again, it's a function of the spectral bands. And if you're interested in surface-to-surface radiation with multiple spectral band, then this is another tutorial that we have on our website. And this is a tutorial demonstrating the greenhouse effect. On the left, you have a black box covered by a plate made of glass. And on the right, you have the same box, but covered with a fully transparent plate made of plastic. So the difference is that on the left, you have greenhouse effect because the infrared is trapped and you see the color showing a higher temperature, while on the right, you get less lower temperature just because the glass is transparent to the infrared. So the radiation can leave the system. Okay, so I promise that I'll make a live demo of Comsol multiphysics so that you can really realize how it works. So for this, I'm showing one of our favorite example for demonstrating purpose. It's a chip here that is covered by a heatsink, and we want to model how the energy dissipated by the chip is dissipated by the heatsink, both by convection and convection, and also by radiation. And this is a tutorial I like to demonstrate that in case of moderate airflow, which is the case in this model, if we account for surface-to-surface radiation or not, we get slightly different result. On the left, you have no surface-to-surface radiation, so energy just dissipated by the flow, and you get a maximum temperature 85 degree. While on the right, with rather high surface emissivity, about 0.9, you get a temperature increase that is 10 degree lower. So yeah, I'm sharing my screen. I hope you can see now Comsol multiphysics. So we have very short time, so I'm going to show you Comsol multiphysics. So when you start the wizard, you can select the dimension, you can select the physics. So here, conjugated transfer. I'll start with, I solve the easiest one, laminar flow. When you have, you can also add surface-to-surface radiation, so you get all your model. Then you can decide the type of study you want to solve for, stationary in this case, and then you start your model. So in order to save some time, still I'm going to load a model where this has been done, and also the geometry has been defined, so that we don't spend time on that. So that's a model just with the geometry, as we can see here. We also have the material that have been defined. So we have a heatsink that is made of aluminum, the chip, the surrounding air that is here, the emissivity for the heatsink and for the channel walls. So yeah, the physics has disappeared. So I'm going to add it again. I click just here, add physics. And here you recognize the same menu. So I pick the physics I'm interested in. So laminar flow. In the radiation, I pick not the participating media, but the surface-to-surface radiation. I can close that. Here, if I expand the mode, I can see that there is a coupling for non-atomic flow. There are more couplings available, including heat transfer with surface-to-surface radiation. But I can enable on all boundaries, and now I have my free physics and the corresponding coupling. So now to proceed, I can select any node, and for example, if I want to enrich the heat transfer model, I can select the node and define the property. For example, by default, there is no fluid defined, so I can pick the air channel and just say that this is air. So now I have solid there. Of course, I want to define a heat source, which is available here. That's for the chip. It is available here, and I just have to type either heat source in watt per cubic meter or heat rate. I say that it's 10 watt for the whole chip, and let Comsol decide what is the density. Of course, we have to define the inflow in the flow condition. We can pick the inflow boundary. We need also to define outflow. That's for sure. And I believe we are done with heat transfer. Now, if we go to laminar flow, we don't have much to do. The most important thing is to say that it's only in the air domain and not in the solid, of course. And we have an inlet, same position. So we have different way to define the inflow condition, and I will take fully developed flow with average velocity. And here I can either type quantity or use one of the predefined parameter that were present in my model where I loaded. And I will also set outlet condition here with a 0 relative pressure. I believe that's it for laminar flow. And for surface-to-surface radiation, I'm going to do something very, very plain again. So here as well, the material property has been already defined, the material node. I will say that I have different surface everywhere, but on the inlet and outlet. So for this, I have a selection of boundaries where all the boundaries that are radiating are selected, but the inlet, outlet, and also the one below are not selected. And if I want to have a better view, maybe I can hide some boundaries so that I can see what's happening inside. The only thing I have to do is to say that the exterior to the radiating wall is opaque. So I pick opacity and say that the void, which is external to the geometry, are opaque. So with that, I can define a mesh. So by default, I will get some kind of mesh. In order to be fast, I will remove the input given by laminar flow physics interface to the mesh. So all, as you can see here, all the physics interface are contributing to the definition of a mesh. And of course, the laminar flow will require find a mesh close to the wall. I'm deactivating this to save time. So that's not good for accuracy, but that will make it possible to solve within a few seconds. So in order to solve, I have to add a study. I will request a stationary study. And here you can see that all the physics are solved for. I just press compute. I hope all my model has been set up correctly. If not, I'll get an error message quickly. Let's see. And if it works, I'll get some convergence plot as it's progressing. So we see, yeah, I have a progress bar here. Yes, I have a convergence plot. So we have three different curves. So we have error estimate for radiosity, for temperature, and for velocity and pressure. So if everything goes well, it will decrease till the requested tolerance, 1e minus 3 by default, and display the results. Okay, it seems that it has been working. We have a number of default plots. So here, for example, we can see the temperature with the temperature color range here. We can see it as isothermal contours. We can see the pressure variation, or we can also check surface radiosity. Okay, I'm stopping here. I want to keep sharing some information about the other capabilities, and I guess that this change is a very important one. So Comsol provides a number of predefined approach for phase change. One is called apparent heat capacity. So this is an implicit way to define phase change by changing the definition of the heat capacity and adding contribution due to the phase change. So that's something that is predefined in Comsol. Another approach is based on ALE, arbitrary Lagrangian method. So in this case, you have moving mesh, so big difference. This one is very accurate, but has no support for a topology change, but the main difference with the first approach. We have also models for irreversible transformation, damage, curing. So this is also coming as predefined option of physics interfaces. We have dedicated interface for something that is probably the most common phase change we are facing in the daily life, moisture transport. So we have a predefined interface here. You can see a glass filled with water exposed to a flow, and we are computing the relative humidity and evaporation of the glass surface in this model. And this is the same kind of physics. I mean, phase change evaporation is the base of heat pipes, and heat pipes relies on the fact that you get evaporation on the heat source, condensation on the cold source, and liquid water or another fluid migration in a porous material, which is usually weak, surrounding the vacuum chamber. So if you're interested in this, I guess we have a very good example showing how you can model it. So it's a comprehensive approach with laminar flow in the vacuum chamber, bring an equation in the weak heat transfer in porous media to cover both heat transfer in fluid, porous media, and actually as well in solid. And what I like very much in this model is that all the material property are defined from our thermodynamics database. So it means that we are really advanced property to get a correct description of all the physical property from conductivity, density, but also latent heat of evaporation of the water. Okay, and a few words about multi-physics grouping. We focus very much on heat transfer and flow, but as I showed in the introduction, there are many other modules in Comsol multi-physics, especially for electromagnetic physics. So we have predefined grouping for Joule heating, induction heating, microwave heating as well. And if you're interested in energy harvesting, for example, maybe you're interested also in thermoelectric effect. And Comsol has built-in functionality for Peltier-Seebeck and Thomson effects. On the structural mechanics side, if you combine heat transfer with structural mechanics, then you'll get automatically the coupling. So the structural stresses and strain resulting from temperature change in the model. And if you also include the flow in your model, then you can account for fluid structure and direction, FSI. And here you have different approach depending on the magnitude of deformation. Either you will want to work with a fixed geometry, which is rather inexpensive, or you want the full accuracy with moving mesh. And in this case, you can go for large deformations. And to conclude this presentation before the Q&A, just a few words about optimization. So maybe you recall that there is add-on product for optimization, and there are different ways to tackle optimization. Either you parameterize your model, and in this case, in particular, the geometry, and in this case, you can have a very accurate representation of the physics, and you can tune different physics parameters to improve some performance, to improve some objective function. Another option is to use shape optimization. In this case, you don't have a set of scalar variables, but you have really fields of variable for the shape of your geometry. And here we have a plate heat exchanger. So we have a cold and hot fluid flowing on each side of a plate. By default, the plate is flat, but in this model, we are looking at the effect of deformation on the efficiency of a plate heat exchanger. So here you can see a magnified deformation of a plate, and yeah, here you see while it's solving, you can see the objective function that is oscillating a bit, but still increasing till find the optimal shape for the system. And here you see the difference of flow for the cold and hot fluid on the initial flat configuration of the lathe versus the optimized configuration. You can see that it's very different, hence the difference of performances. And I know the last option is very famous. It's the topology optimization. It's extremely creative. It's also very challenging from modeling and commercial point of view. That's also something you can do in Comsol multiphysics. And here we have an example of optimizing channels. So we have inlet here for hot fluid, another inlet for cold fluid here, and we have to define the path for the two fluids so that we optimize the exchange heat. And so this model is doing this based on.
Nicholas, if you can wrap up in 1 minute, we'll take some few questions.
Okay, so I'm going to conclude just to show that this kind of model can be done with a different regime and give different results. And yes, let's bring us to the last slide, and yeah, I will be happy to take any question.
Very nice presentation, Nicholas. Like you showed a live demonstration using a radiation problem. Are there any questions from audience, volunteers?
At this point, there are no questions. Maybe we can just wait for 1 minute.
Okay. So I have a question, like a general query regarding this moving mesh and multiphysics coupling of a problem such as if you consider atomization of in powder metallurgy. So many things are happening, like a molten liquid is flowing, a shock wave is coming, and there is a flow of the liquid also, then there is a solidification also. So multiphysics, if we invoke, so it's automatically coupled, like three physics are coupled, or we have to do it manually?
Okay, so as we briefly saw in the physics interface, we have a set of predefined physics. Maybe I can go back here. So there is a library of predefined physics. For example, for if you go in structural mechanics, you will find free structural interaction. But all the combination are not predefined because it would be a huge list. But what is available is assume you have a heat source coming from electromagnetic heating. Then as soon as you get another physics, you will get here a list of all the sources that are defined. And so and that's the same for all the physics. If you have a temperature that is defined and you have a temperature dependency in another physics, then you will be able to pick in this drop-down list all the inputs that are defined by all the physics. So it's predefined in some cases, and in other cases you get like an assistance to pick the contribution for each physics and to match them together.
So user-defined functions we can add in like in C programming, or there
yes.
is in the
No. Oh no. You don't need. Okay, if you really want to program, there are a lot of options to program, and there in this application builder you can switch to development mode. But if you have something as simple as like a cosine function of t, you just type it. If you want the time derivative of space derivative of t, you just type tx, and that's the spatial derivative of t. If you want the second order derivative, you type txx like this. So you have a lot of things you can just do by typing. And if you are really keen and comfortable with equation, you have this equation view that I also mentioned, and you can go there. And if you are familiar with equation, you can see all the equation we are solving, and you can type, modify them, and next time you solve, then you get this sign saying, okay, you are doing something that is on your own, but when we are solving the equation you have defined, we are no longer solving the default equation. So it's in most of the cases, you really don't need to program. You do everything in the user interface.
Okay. So I think if there are no audience questions, we'll wrap up the session here.
Okay, thanks again very much.
Thank you, Nicholas, for this nice presentation. So we'll end the session now. Thank you very much. Goodbye.